So I'm blue. Right, so this is our schedule. We're going to talk about pumps for about an hour, hour and a half or so, and then talk about diesel gensets, instrument air compressors, nitrogen generators, control schemes, things like that, all of which we delve into when we buy large packages of rotating equipment. First, we have our safety moment. And since controls is one of the topics that we're going to talk about today, I wanted to talk a little bit about equipment controls and give you a story about how they can and can't help you. We buy control systems because they're for machinery monitoring, control, and protection, which means that it will keep the machine from getting either in an overspeed, over temperature, an overpressure, or an over torque condition. Obviously, all of these, when you exceed the design parameters of a machine, you end up increasing the stress levels beyond the original design point, which will cause failure. Overspeed puts hoop stresses in the rotating section of the machine, causing a failure of the rotor, which is about the worst that can happen because you end up having pieces leaving the machine with high velocity. Over temperature will reduce the material strength to a point where failures will happen. Overpressures will overstress the stationary components of a piece of machinery.
Sorry.
Beyond the material strength, causing failure and loss of containment of the process gas. And over torque will exceed the material strength of the drivetrain, which could cause a failure at any location within the drivetrain, either inside a piece of machinery or between machines if it turns out that the coupling is the part that's going to fail. For some installations, the machinery control panel that comes with the equipment skid also controls the process and the process isolation valves. For example, on a compressor, the control panel will control the surge valve. And in some instances, the turbine and the compressor control panel will also control the way the process loop is purged to inert it prior to startup, the way that the machine is brought up to speed and the loop's brought up to pressure, and then brought online by opening up the isolation valves. All that can be programmed into the machine control panel. However, there are some philosophies and some clients that like to have the isolation valves controlled by the plant safety system, sometimes called an SIS system. And the understanding is that the plant safety system is considered more reliable for plant and personnel protection than the turbine control panel. The belief being that the turbine panel is dedicated towards the turbine of the compressor operation, not to the plant, whereas the plant SIS system is dedicated to the plant and to the people, and so more appropriate for isolation control. This is one of the CGF GHX2 gas turbine compressor trains. I've shown you this slide a few times before. This is a single shaft gas turbine driving directly into two sets of compressors. It's very large, 60,000 horsepower machine, so there's a lot of energy potentially within this machine. As you recall from our last session, we talked about degradation that occurs to gas turbines, the part that you can't get back and then the part that you can by washing. And so at least once, if not twice a year, just about every gas turbine is going to be brought down up in Alaska to do a water wash to clean the axial compressor. This has to be done during the summertime because in the wintertime the water wash will just freeze inside the engine and cause some severe damage. But what this does, it requires the gas turbine to be shut down and then cooled off, so it has to be down for about a day. And for the older machines, like the machine that we're talking about, this is a manual operation. On the newer machines, you have it completely plumbed up so that water with a detergent is sprayed directly into the engine. Spinning the engine at slow speed will wash it, and then you go ahead and drain it automatically without having to go inside the engine. But on this machine, you take this panel off and you walk inside the inlet plenum to gain access to the front end of the engine. Obviously, the engine is shut down and isolated. The fuel system has its blinds swung, and all the electrical systems are de-energized while you're doing this operation. but sometimes things happen. You can see where this man is standing. You know, up on the front end of an axial compressor is the #1 bearing, and then there's struts which support this bearing inside the casing to keep it in place. This is the process loop for the compressors of that gas turbine compressor train. You can see the gas turbine here, directly coupled to the low pressure and then the high pressure compressor. At the point in time this valve was closed and that isolation valve was closed, the entire loop had been depressurized down to the flare, but there had been no blind swung because all of the operation was taking place in the gas turbine, which is physically isolated from the compression loop. So while lockout, tagout had been done on the gas turbine fuel system, there actually hadn't been any done on the process loop system. So while the man is inside the inlet plenum spraying soapy water, he's using a pressurized plastic container, and if you guys have ever sprayed around your house for insects, it's the same basic concept. You pump it up with air and you spray. So he's in with his wand, he's spraying soapy water on the inside of the engine. And unbeknownst to him, up at the main process control system, the DCS, there was a programmer working on a completely different system, entering code in and trying to debug it. And unfortunately, he entered in a wrong line of code by accidentally typing it wrong, and he swung that isolation valve open. Well, this entire loop, volume-wise, is pretty large, and it's at atmospheric pressure. This is now a high-pressure gas source, which is now flowing into the process loop through the compressors, turning them into an expansion turbine. And it ended up spinning the gas turbine up to about 1,500 RPM. And when this axial compressor spins, it's going to pull air. And it actually had enough air velocity across it to pin the operator against the struts that are holding that front bearing in place. And it held them there for a long time because you don't see them here, but there's vents off the flare that were open so that the process loop would never build up any pressure, so the gas was happy to stream right through and then back out the flare. So he was pinned inside, this thing's spinning at several, 1,500, 2,000 RPM, and he can't move. The other operators who are in the area suddenly become aware that he's in great distress, but there's not much they can do because the control panel for the turbine has been isolated and shut down, so they have no control over that valve. And the way that they finally ended up stopping everything was to actually go out to this valve and disconnect the air source to the actuator so that its spring would return it to its fail-safe position, which was closed. And I think they ended up taking that instrument air connection off with a hammer. So once that valve was closed, then this eventually coasted down to a stop. And they were able to get the guy out. He had bruises from where he was brought up against the struts, but other than that, there was no harm done to him. And for some miraculous reason, he was able to hang on to the water wash bucket and the spray nozzle, so there wasn't any material actually went through the gas turbine while this was happening. But it was a rather frightening experience for him, which you can understand. This is a picture of the same engine. You can see the struts he'd be pulled right into. So, yeah, the turbine was considered de-energized, and the ice-related systems were locked out and tag out. And I guess what I want to get across is that not all hazards are covered in a HAZOP. There's no way that you would consider this kind of a failure or a hazardous situation in a HAZOP. And I've been in several, and people come up with what you would think are the most unrealistic situations, and they would still never approach what happened to this operator. So seemingly isolated systems can suddenly interact without your knowledge, and the outcome can be a dangerous situation. So when you guys are in HAZOPs, don't disregard any of these seemingly ridiculous scenarios that people come up with, because worse things have happened. Yeah.
There are no optical sensors inside that detect any foreign objects? Because you mentioned
No. If you tried to measure, then the reason is that you've got a horrendous amount of air going into the axial compressor, and if there's any foreign object that's in that gas stream, it's going by so fast that it's almost invisible to the naked eye, so it's going to be almost invisible to any sensor that's trying to pick it up. And even if you had sensors there, by the time it comes into a sensor range, within a quarter of a second, it's into the engine. So you don't have any reaction time to work to it anyway. And even if you shut the fuel off, these machines take between 6 and 10 minutes to coast down to a stop. So you're still going to have internal damage during that coast down time. Philosophical moment. You guys remember the elephant? Back in the 1980s, Malaysia had a sudden increase in the energy requirements, electrical power requirements. And so they contracted the General Electric Company to supply them with several gas turbine generators to spread throughout the country to help, meet their needs. And so I was talking with a field service guy that went in and watched the installation of one of these units. And he had gone over to Malaysia. He'd flown over to meet the equipment as it arrived on ship, and he went down to the wharf, and he met the ship, and he wanted to do an inspection on the equipment before it got off-lifted to make sure it got through the ocean transit okay. And generally, the gas turbine itself, gets saran wrapped before it goes onto a ship and comes across. And so all the equipment came across okay. And so then he was pretty much expecting to see, he waited for a truck like this to show up so you could offload the turbine down onto it and take it up to its site. Well, the site for this was up in the hills. The Malaysian engineering company that was doing this had decided that it was easier to make the location up in the hills rather than where the gas source was, and just run the electrical cables down, rather than run a gas pipe all the way down to where an alternate source would be. So this had to go up, partway through the jungle to get to its final site. So as he was waiting, he noticed that there were a couple of light trucks that showed up with a whole bunch of logs on them that they deposited up next to the ship, and then all of his light equipment started to get offloaded. Inlet filters, inlet ductwork, exhaust ductwork, fire suppression, lube oil coolers. There's a whole bunch of things that go along with the gas turbine that aren't heavy. And so all these trucks that brought the logs in, they offloaded the logs, they picked up the stuff, off they went out of sight and off to the site. So he was waiting for a big truck to show up. And he noticed that a crew of about 30 guys came down, and they started to take these logs out of their bandings and laid them down next to the ship on the wharf. That was strange, because if they're going to load them onto the ship, they should have left them banded. And then he heard the crane on the ship fire up again, and they started to pick his turbine up. Well, I don't know where you're going to put it. There's no truck down there. So they dropped it down onto the logs. And then down from the end of the wharf came 12 elephants, all in harnesses. And they walked them down, and they harnessed them up to the turbine and to the generator, and they walked them on the logs along the wharf into the town. Now, the crew of guys was still there, and every time a log came out the back, they'd pick it up, and they'd walk it up, and they'd put it in the front, and they trundled that turbine and that generator, one right behind each other, down the wharf, through the town, and then up the trail, up to its site. It took about 6 days for them to get there. But they got there. And so, I always loved that story, and because to me it's important to remember that sometimes the old technology does actually still work, and just because it's not new and high tech doesn't mean it's not the right way to do it. And any tools you use properly, even if they're old, will do a good job for you. So let us talk about the quiz that you guys took and finished from last class. Now, the majority of the questions I figure you guys breezed through without any trouble at all. The ones that might have given you problems were on the graphs on the gas turbine. So we'll go over those. So the first question was, what's the heat rate of at a certain ambient temperature at a certain horsepower? And so the first thing you had to do was to find the chart that had the right ambient temperature, and we identified 20 degrees Fahrenheit. And then the second thing that you would have to do was to convert either the ISO rated power of 43.7 to the site rated power, which would be with your inlet and exhaust losses, so you'd subtract 2.2%, or you would change the horsepower that I gave you to an ISO, semi-ISO condition by adding 2.2% to discount the losses in the inlet and exhaust. So that would give you a horsepower that you could compare. So if you took the horsepower that I gave you and then added the losses to get the pseudo-ISO conditions, you would get 45,879. You would then compare that to the 43.7, and you would find out that you were at 105% of the design horsepower of the turbine. So then you come across your line at 105%, and I gave you a 95% speed. And if you come up and on the 20-degree ambient, you find that you are right at 100% of the design heat rate. But that's not quite the whole answer, because with the 4 inches of water inlet and exhaust losses, you have a heat rate adjustment of 0.6% for each inlet, for the inlet and the exhaust. So your final number would be 8511 BTUs per horsepower hour. Some people probably took it out to be a little bit more difficult than that, but that's how you would use these curves. Just for information, I wanted to find out, how much fuel are we looking at. So we're looking at 9 million standard cubic feet of gas a day. The next problem was to determine at what ambient temperature you would exceed 50,000 horsepower. And so first you would change, with the inlet and exhaust losses. So first thing you do, you change your ISO power to your actual site rated power with your exhaust losses. So you get 42,742 when you subtract your 2.2%. And you divide that into 50,000, and you find out you have to be at 117% of your design power to get to 50,000 horsepower. So on that, it's either the last or the second to last curve in your handout, you have 117% of the design, and you come across to where you cross your output curve and you drop down and you find out that it's at about 13 or 14 degrees Fahrenheit. That was pretty straightforward, right? Good. Does anybody have any questions on any of the other questions on the quiz that we should talk about for a moment? Nope? Okay. Let's talk about pumps then, since that's why we're here. There's 3 basic types: dynamic, positive displacement, and there's a couple of new styles that are coming on the scene that have some interesting features about them. On the dynamic type, we've got centrifugal and axial. Positive displacement type, we have reciprocating, diaphragm, gear, screw, progressive cavity, and metering. The new ones are multi-phase and downhole. This is a chart that shows kind of how they're broken down. There's also a group that's called the special effect, which are the adductors and lift gas style, which inject gas into a fluid stream and bubbles the fluid to the top, acts as a pump, but there's no moving parts. You might notice that there's a lot of similarity between this and the compressors that we were looking at the last class. And that's actually not an unreasonable expectation. You have some of the same problems, how to increase the pressure of a fluid. You have some of the same physical properties, and so it's not unreasonable to expect that the results may look fairly similar as well. So motor-driven centrifugal pumps, or centrifugal pumps, can be driven by a motor or a turbine. You have a motor-driven single-stage pump or a multi-stage pump. This is a motor-driven inline pump. The pump is actually at the bottom of all of this. It's called inline because it actually sits between the 2 flanges on the pipe, just kind of on a little concrete pedestal to take the dead weight. As the pipes move because of thermal growth or other strains, the pump follows it around, so it'll physically slide around. So it has to have flexible connections for the electrical system, and anything that it can't have flexible connections have to be physically mounted on the pump itself someplace. Air-driven double diaphragm style pumps. This one is good for relatively low flows and low heads, but as a sump pump, they're stupendous. Motor-driven reciprocating pumps. You'd have the motor out here connected to the drive shaft. The pistons are in this area here, and then the actual pumping takes place here. Motor-driven sump pumps. These there's a flange. It sits on top of a platform, extends down into the liquid pumpage. You can either have the discharge below your platform or above your platform, depending on how you want your piping to be routed. Motor-driven vertical, this is a vertical turbine pump, sometimes also known as a vertical can pump, because there is a physical shell around the pump itself. Fluid pumpage comes in, goes down to the bottom of the shell, the pump picks it up here, pumps it up and out the discharge side. This is used for low NPSH conditions. And then the downhole pump. This is the motor, and that's the pump. There's the suction strainer. This is actually physically lowered down inside a well to wherever the bottom happens to be. It's got a pipe that comes out, and it's got a power cord that comes out, and it just rests down at the bottom of the well and pumps fluid from down there up to the top of the well. So that means obviously you've got a very, very long hose and a very, very long cable if your well's down about 5,000 feet. Takes a special rig to be able to drop them down that far. They're kind of new experimental. BP's experimenting with them to see if they'll work reliably. So far, they've got about a 50% reliability on them. If we're going to talk centrifugal pumps, there's a couple of terms that you need to understand and know about, which you may not have been exposed to before. The first is cavitation, and that's the formation of vapor bubbles in the pump inlet and on the impeller. The second one is the NPSHR, the net positive suction head required, and that's the pressure required at the pump inlet to avoid cavitation. NPSHA is the net positive suction head available. That's the pressure available at the pump suction from the process. And priming, and that's the ability to pull fluid into the pump. We'll talk about priming first. Let's say we've got a tank, above grade, sitting several feet above a pump. We're taking fluid out of the tank, into the pump, and it's being pumped someplace else. The fact that this tank is physically over the inlet nozzle to the pump means that the fluid will gravity feed straight into the pump. That's known as a self-priming system. All pumps will operate this way. That's the way we like to see them. Can't get them that way all the time, though. If the tank is underground, physically below the inlet nozzle to the pump, and is pressurized, depending on the pressure inside the tank and the specific gravity of the fluid and the elevation difference, this could be self-priming, it may not be. If there's enough pressure to have the fluid rise beyond the pump, then it becomes a self-priming system. If the fluid only comes up this high, then it's not self-priming, and you have to figure out a way to prime it. Obviously, if you've got a reservoir, a tank, a pump, or a pool of some nature, that the fluid level is below grade and it's open to the atmosphere, the liquid level is here inside the suction pipe, and there is no way of pushing it up into the pump suction. This is a non-priming system, so that means you have to form some external source of prime to be able to get the fluid into the pump so the pump can operate. And you do that, one way is to pull a vacuum on the discharge line so that it actually pulls the fluid up through the pump and up to about this elevation. An alternative is to have an external priming fluid which floods the inlet line so that it becomes so full of fluid traveling in both directions that it becomes primed, and you go ahead and start the pump. You start pulling fluid out of your sump, and then you go ahead and shut your priming fluid off. This works reasonably well if you've got relatively small line sizes, 2-inch, 4-inch. If this is a 20-inch line, you're talking some huge flow rates to be able to fill that line up because there's no restriction at the bottom, and it's going to go to the passive least resistance. So conceivably, if your level is high, you can overfill your sump before you actually get the pump up and operational. So let's go back to our nice system, gravity feed. The tank is above, physically located above the pump. And that's the envisioned way of having the system work. But when it comes time to actually physically lay the piping out, you know what, I've got a pipe rack I have to get the pipe up onto. Or there's a door here that I have to not block. So now you've got a high point, which could physically be over the liquid level inside the tank. So obviously the liquid level inside the pipe will never get above this point. So you've got a non-priming system, even though the tank is physically above the pump itself. One of the corollaries to that is if we have a high point into the pump suction that's below the fluid level, it will be self-priming. But in this location here, you're going to have trapped gas, which needs to get vented off. So we need to have what's called a high point vent. The operators will open up until fluid passes out of it to get rid of any trapped air that may be in that location. And they'll do that before they actually start the pump up. So on centrifugal pumps, how does the pump operate? Well, you've got a spinning impeller, and fluid comes in to the center section of the impeller and gets pushed outwards by these vanes that are rotating at a high speed, which imparts velocity to the fluid. Again, using Bernoulli's law, you have a slight drop in the static pressure as the fluid is accelerated, and then it starts to build up static pressure as well as velocity head as it travels out through the impeller. And then out here in the stationary section is slowed down again to generate the static head from the velocity head that's been imparted by the impeller. That's what one of the impellers is going to look like. Not necessarily big. These are generally cast with not a lot of machining done on them, a little bit on the outside diameter to get them to whatever size and shape, final shape you're after. So this is a fairly typical outline or sectional view of a single stage overhung pump. We have an end suction, a top discharge, and that's probably 90% of the pumps that you guys are going to see, because that's 90% of the ones we buy. The driver will be out here. You've got your input shaft, 2 sets of bearings with a dipping ring oil system. Then you've got your shaft seal. And then the shaft seal inside what's known as the stuffing box. You'll have perhaps a throat bushing at this location, and then the actual physical impeller sits right in here. So the flow comes in and out. The way that the bearings are lubricated, like I said, there's a dipping ring lubrication system, is that as the shaft spins, there's a larger ring that's just sitting on top of the shaft, and as the shaft spins, this ring also rotates. And it rotates down into the oil reservoir at the bottom of the bearing housing, which picks up oil from viscosity, brings it up and deposits it on top of the shaft. And then from there, it moves along the shaft and goes out to the bearings and lubricates the bearings. It's a nice little system, very reliable. Not a whole lot that can go wrong with something like that. So here we have the inboard bearing, and here we have the outboard bearing. This is a single cylindrical roller bearing. This is a double ball bearing, and this is going to carry the thrust. And then we have this long overhang to get to where the impeller is. And I don't know, but if anyone else thinks about it, but when I see that, I think something like that, where you've got an anchor point here, an anchor point here, and then the impeller's out here trying to bounce around. So we spend a lot of time and effort trying to make sure that this is stiff enough that the impeller can't afford, is not allowed to move, is constrained by these bearings. But you can see, because of this long overhang, it doesn't take much motion at the bearing locations to have quite a bit of motion out here at the impeller. And as you recall from the seal discussion that we had at the last class, the seals are extremely close fitting parts, very high tolerance parts, and so relative motion between the two can cause them to not seal as well as they should be. So a couple of different styles of centrifugal pumps. This is what's known as a double suction pump, where you have flow coming in, and the flow is actually split, and it goes into a back-to-back impeller on the common shaft, and then comes out a common discharge. This is for extremely high flow rates. If you want extremely high pressures, you end up with a multi-stage pump, which operates in a similar method to the multi-stage compressor. Each wheel imparts